Welcome back to another section in Chapter 8. Today we're going to be looking at rational functions. We've been adding and subtracting, multiplying and dividing rational expressions. Now we're going to look at graphing them. So we're going to have y equals or f of x equals for some of these. And there's going to really be two big types of rational functions. And we'll do different things with each type. Our learning targets, the first one is I can graph rational functions. That's one of the types of functions we'll be using is about graphing, and that'll be the second one we'll be dealing with. The other learning target is I can transform rational functions by changing parameters. So this is where we're going to be talking about the transformations that we'll do with these rational functions. We won't have a specific section for the transformations. It's just part of this, and we're not going to go as in depth in transformations as we normally would. And we're going to look at the transformations first. And so, with our transformations, we're going to start out with the parent function, f of x equals 1 over x. This is just the inverse variation function with a k-value of 1. Our transformations are going to take it to g of x equals a over x minus h plus k. And each of these things, we should kind of know what they do with. For instance, a is a stretch, right? A is always a stretch. Hey, we're multiplying it to the function itself. Notice I did not put vertical stretch. It's actually a vertical or a horizontal stretch in this case, which is kind of fun. These don't stretch so much as they're going to dilate. A could also be a reflection if it's negative, to make that fraction negative. And again, doesn't matter if it's horizontal or vertical, it reflects it both ways. And then h, x minus h. H is a horizontal translation. And then k is a vertical translation. So we're going to be moving it over h and up k, just like we've been doing all the rest of the time. And this is our transformed function. And so let's look to see what the graph of this looks like. The graph of 1 over x just looks like this. We saw this when we were looking at inverse variation functions. Notice 1 times 1 is 1, 1/2 times 2, 1/3 times 3, 1/4 times 4, and then same thing with the negatives. If we wanted to do a stretch to get that a, say f of x equals 9 over x, that's going to pull the graph away from the origin, and it'll look like that. And keep going. The bigger this number is, the further away it'll be pulled. If we zoomed out, it would actually look the same as the blue one, but we'd have to take the blue one away. So how about one where we're actually moving it? Let's go f of x equals 1 over x plus 4 plus 3. Thinking about our transformations, that's going to move it 4 to the left, because remember that negative, this is an x minus negative 4, so it'll move it 4 to the left and up 3. So it's going to take 4 to the left, up 3, and it ends up right there. And so now looking at this transformed one, the red one, we can ignore the other ones. I'm not going to take them away, but we're going to look at the red one right now. Each of these has two different asymptotes. These are also called hyperbolas, which is going to be kind of weird because in Chapter 10 we're going to see another shape called a hyperbola. Hyperbola is used several times in math. But these have two asymptotes. First, it has a vertical asymptote at x equals h. In our case, it's x equals negative 4. And remember, an asymptote is a line that's going to get closer and closer and closer to without ever touching. So we have a vertical asymptote at x equals h, and we have the domain. X can equal anything at once except for that value. Then we also have a horizontal asymptote at y equals k. Notice it's getting closer and closer and closer to that, but not touching it. And the range y will equal everything except for that value. So y doesn't equal k. And then these functions, we have a couple vocab words here. One is a continuous function. A continuous function is a function that does not break. Pretty much every function that we've ever dealt with, lines, quadratics, polynomials, exponential, logarithmic functions, you can draw them without lifting up your pencil. That's continuous. These guys are discontinuous functions because they have a break in them. It goes from here, it goes down, and then it starts up there again. And there's this hole where it's not touching. That would be a discontinuous function. We'll be seeing a few more discontinuous functions in Chapter 9, but this type is also one. Does that mean much? No, except that the domain has a number in it that it can't equal. So this is what we're going to work with transformations. Yes, you're going to be graphing them, but when you graph them, I'd start out with, where are the asymptotes? Hey, we moved left 4, we moved up 3. I'm going to put my asymptotes there. It's a positive, and so we're going to sketch the graph where it needs to be. The other type of rational functions we're going to be dealing with look like what we've been adding, subtracting, multiplying, and dividing. They're going to look like a polynomial divided by a polynomial. And what we're going to do is we're going to find the zeros, the vertical asymptotes, the horizontal asymptotes, and the holes in the graph. None of these are very difficult to find, and we've pretty much found them all. We just haven't known that yet. So we're going to start with our rational function. It's just a polynomial divided by a polynomial. The first thing we're going to look at is the horizontal asymptotes, which is what the end behavior is. No, I don't have a dance for this one, sorry, but it's the end behavior. This is the most difficult looking to find, but it actually is really, really easy and takes almost no math at all. So what we're going to do is we're going to look at the degree of both the top of the fraction and the bottom of the fraction. And remember, the degree is just going to be the highest exponent in each of the polynomials. And then we're just going to play the what number is bigger game. If the degree of the top is bigger than the degree of the bottom, then there's no horizontal asymptote. So for example, if we had something like f of x equals x squared plus 3x plus 2 over x minus 3, the degree of the top is 2, the degree of the bottom is 1, so there's no horizontal asymptote. What does that mean? Well, this is the end behavior. It's when x is going to infinity. As x gets really, really big, this x squared gets really, really big, and this x really doesn't mean anything, neither does this 2, or that negative 3. All of these mean less and less and less as x gets really big. So as x is going to infinity and negative infinity, we end up with x squared over x, which could reduce to just f of x equals x. So we actually do have an asymptote. It's y equals x. That's not horizontal, it's not vertical. It's called an oblique asymptote. And so if we zoomed out really far on this function, we'd end up with something that looks like a line, y equals x. There'd be a little bit of funky jazz right in the middle around y equals 0, but for the most part, it would just look like the line y equals x. Anyway, if the degree on top is bigger than the degree on bottom, there's no horizontal asymptotes. How about if the degree of the top is less than the degree of the bottom? Then y equals 0. So, same idea. We have our polynomials. The degree on the bottom is x squared. The degree on the top is just x. As x gets big, this stuff doesn't really mean much, so it just kind of goes away. And we could cancel this to be 2 divided by x. Well, as x is getting really, really big, 2 divided by really, really big numbers gets really, really little. It just becomes 0. And so we end up with y equals 0 is our asymptote. And then the third possibility, what if they're equal? If the degree of P equals the degree of Q, then we actually look for the leading coefficients of both the top and the bottom. So if we have something like 2x squared minus 3x over 3x squared plus 5, as the x squareds get really, really big, or as the x gets big, these guys get really big. These guys don't, so they don't matter. I thought I had a box there. There it is. So we have 2x squared over 3x squared. The x squareds cancel. We're left with y equals 2/3. And so we have a horizontal line at y equals 2/3. Now, people have trouble graphing that for whatever reason. They like to make it a slope, up 2 over 3. No, it's just you go up 2/3, about 0.6666, and you make a horizontal line right there. So don't try and make it a slope or anything. And so that's how we find our horizontal asymptotes. There's either none, it's y equals 0, or you look at the leading coefficients. Notice there's no actual math there. It's just, hey, which one's bigger? Which one's bigger? Which one's bigger? And you could do it just by observation. And we'll see that in a couple minutes. So once we found our horizontal asymptotes, we're going to factor both the top and the bottom, and then we're going to simplify. And that is going to help us with our zeros, our vertical asymptotes, and our holes. For the zeros, so we have a fraction now. What would make a fraction equal to 0? If you have 0 divided by something, that gives you 0. So we just need to make the top 0. So 1 is the top 0. For vertical asymptotes, that's where x can't happen. Well, what would make a fraction where it can't happen? That would be when the bottom equals 0. And then the holes are those factors that we canceled. What's simplified? It was 0 in both the top and the bottom. That becomes a hole. And a hole is somewhere where the function should be, but for whatever reason it's not. It's just a little blip that's not in the graph. And we'll see how to graph those as well. So let's look at graphing some of these. Start with the function f of x equals x squared plus 3x plus 2 over 3 minus x. First step, horizontal asymptotes. We'll look at the degree. We have squared, and we have just 1x. The top is bigger than the bottom, so there's none. Our oblique asymptote, if we were looking for that, would be x. It would actually be a negative x because that negative. And so if we zoomed out, it should look kind of like that, or it's just going downwards. Now we can factor and simplify. So the top factors, x plus 2 times x plus 1, but there's nothing to cancel with 3 minus x. Even if we factor out the negative to make it x minus 3, still nothing to cancel. So we can find our zeros, our vertical asymptotes, and our holes. The zeros are when the top equals 0. Let's see, the x plus 2 equals 0, so x would equal negative 2. X plus 1 equals 0, x equals negative 1. So we have zeros at negative 2 and negative 1. Our vertical asymptote would make the bottom 0. 3 minus x equals 0. Add the x, so x equals 3. And the holes, nothing canceled, so we don't have to worry about any holes right now. So to graph this, we're going to start out with a graph. I'd say appropriately sized. This one is appropriately sized for the values that we have, but we'll actually find out that the graph itself is going to be much, much bigger than this. Anyway, so we have this. We can graph our asymptotes and our zeros. We'll start with the zeros. We have x equals negative 2 and x equals negative 1. So we get our points there. We don't have a horizontal asymptote, but we do have a vertical asymptote at x equals 3, right there. And then we can graph our thing. We can plug in values to see what would be, if it's going to be big or little, like positive or negative. So if we took a value like negative 6, See, that would be a negative times a negative is a positive. 3 minus negative 6 is also a positive, so that's going to be big. Then it's going to hit 0. And it's going to go negative. It's going to hit 0 again. And it's going to get really big. And then down here, it should be negative the whole time. The graphing calculator can help with this, especially when we get a lot of like asymptotes and zeros right next to each other. The graphing calculator can be very useful in figuring this out. But it's important to have this stuff graphed first. Otherwise, you might not be able to make sense of what's actually happening on the calculator, especially when we get into bigger problems. But we can use that to help, and we get, look, something kind of like this. Hey, it goes that way. But I said there should be something down here too. If you remember back a little bit earlier, I said that this graph is good for this, but it's not really good for the function as a whole. If we zoom out here, we're going to see that our graph looks kind of like this. We're looking at this part right here, but we zoom out, we have here's our asymptote, and then it comes down here as well. So that's kind of a weird one because it's pretty big. The problem I took this one from didn't actually have graph as part of the instructions, but I wanted to graph it anyway. So let's look at another one. Let's go with f of x equals 5x plus 2 over x plus 1. First thing we need to look at is the horizontal asymptotes. Hey, we have the same degree, which means we look at the coefficients, 5 over 1, horizontal asymptote, y equals 5. Next, we can factor and simplify. Well, it's already factored and simplified. There's nothing to do with it. So we can look for zeros, vertical asymptotes, and holes. And notice these three, it doesn't actually matter what order you do them in. I'd go horizontal asymptote first, then factor and simplify, then zeros, vertical asymptotes, and holes. So zeros, the top has to equal 0. So we'd subtract 2, divide by 5. X equals negative 2/5. Vertical asymptote, the bottom equals 0. Subtract 1. X equals negative 1. And holes, we didn't cancel anything, so there's no holes again. So now we can graph it. Start out with our graph. We can plug in our 0, negative 2/5. Oh, no, horizontal asymptote first, y equals 5. Then vertical asymptote, x equals negative 1. And then our 0 at negative 2/5. Now looking at this one, we know that it's going to hit 0 here, and it's going to get close to this line. Now, if it went up, it would hit this other asymptote. That's not a good thing, which tells us it should go down, which means just from here, it's going to come up like this, hit the 0. It's going to be an asymptote over here. And then on this side, it won't hit 0, which means it's going to be up here and curving down. That it comes with experience being able to look at that, but it is something that you should think about before just saying, hey, I'm going to graph it. Think about, what do you think it should look like based on the asymptotes and the point? Because sometimes even just plugging these into a graph, into a calculator, can be kind of tricky. But when we plug it in, we're going to get a graph. Looks like that. Looks like what I thought it would look like. We have the piece up here, and then it comes from down here, hits the 0, and it goes over. Let's look at one more. F of x equals x squared minus 4x plus 4 over x minus 2. First thing, horizontal asymptote. Well, the degree again is bigger on top, is bigger than the degree on bottom, which means there's none. Next step, factor and simplify. So when we factor, we get x minus 2 times x minus 2. It'll multiply to give us 4, and add to give us negative 2x. Negative 2x is negative 4x. Then we can simplify. And x minus 2 cancels out. Now we can look for our zeros, our vertical asymptotes, and our holes. The zeros, so when the top equals 0, well, x minus 2 equals 0. Add 2, and x equals 2. The vertical asymptote, well, there's nothing left on bottom, so that's none. And the holes, x minus 2 was a factor that canceled, So x minus 2 equals 0, which means x equals 2 again, which means x equals 2 is both a 0 and a whole. What does that mean? Well, it should be a 0, except there's just a hole there. So there will be a hole at x equals 2 and y equals 0. So let's graph it. We have that. Graph the zeros, and in this case it's also a hole, so it's right there. It's just an open circle instead of a closed circle. A lot of times, like, we'll graph the 0. The holes I wouldn't graph until after you draw it, because you don't know exactly where it's going to be. I'd graph the line and then put a little open circle where that x value is. But we know it's at 0, so we can put it there. And then what is this graph going to look like? Well, this canceled. This is the graph of f of x equals x minus 2. That's just a line. It's a line. It just has a hole right here where x equals 2, because x can't equal 2. That's our domain here. It's from the beginning. X can't equal 2. And so, again, we're just left with a line. If, say, the hole was at x equals 3, I'd graph the line, then go to where x equals 3, and I'd put the little hole right up there. But again, doing that after the graphing step. Anyway, this is the type of stuff you're doing. We're looking at transforming the functions from the parent function y equals 1 over x. And then we're looking at graphing them by finding the horizontal asymptotes, which, if you notice, is a lot easier than what it looks like from the steps. And then we factor and simplify. And then from there, we can find the zeros, the vertical asymptotes, and the holes, which is stuff that we've already really been doing. We just didn't know there were zeros, vertical asymptotes, and holes. And then we can graph it. And so this is what we're doing. So don't forget to leave a comment, and I will see you in class, and I will see you then.